Okay, so let's start. Today we will have the Chalmers philosopher here, but that will be after the break, so I will be lecturing for 45 minutes first, and then he will come here and talk about ethical aspects. Now we have talked about modeling aspects, how to do build up a model of a quadrotor, and how to using these new languages, declarative languages, where you have write down the equations instead. And now we switch over to implementation aspects. So we will talk a little bit about microcontrollers today, and then next week we will start to talk about the C programming language and how to implement controllers using C. And this is a quite challenging to lecture to you, because you have a very different background when it comes to computers and to programming. Some of you have learned a lot about these things, and some of you have not programmed much at all. So I will try to do something that is, at least it will be helpful, I hope, for those who haven't seen this at all, but it will go at a rather fast pace, I believe. But this is something we have to live with when we have a master program, when we have students with a diverse background, which we on the other hand think it's great, of course. Yeah, depending on your background, you need to put a little different effort into this. So I just wanted to start to talk about a little bit about what is the architecture of the Crazyflie. And if you go to the Crazyflie website, you find this picture that shows how what is on the circuit board, which is the frame of the quadrotor here. And in the dark blue here, you have the two main processors. This is what where your control algorithms and your sensor signal processing algorithms will execute. So this one is a 32-bit processor, meaning that every integer is represented using 32 bits, basically 32 binary variables that can be true or false. And it's running at 168 megahertz. And yeah, it has close to 200 kilobyte of RAM and 1 megabyte of flash. And this main processor is then interacting with the IMU, inertial measurement unit, where you have this 3-axis accelerometer, gyro, magnetometer as well, and a pressure sensor. And then there is a standard communication bus called I2C here that is used to connect the IMU with the main processor. It is also interacting with the motor driver through pulse width modulation. So with pulse width modulation, you decide on what is the percentage of the time that the motors will have power. So you will have the main battery with a certain voltage, and then you, by setting the percentage here, or the duty cycle of this pulse width modulation, you basically determine for how long, or what is the percentage that the motor will get the voltage from the battery. So you do not control the voltage directly. Instead, you have a fixed voltage, and then you just decide on what is the percentage that the motors will get the voltage, the fixed voltage. So, but in effect, that would be the same thing as controlling the voltage. Yeah, and then there are also some expansion ports, so you can communicate with the power supply and the battery charger. But I mentioned that there were two processors. So there is also another processor here. So it's a less powerful processor. It's a 16 megahertz Cortex M0 processor. So it's running, so it's an 8-bit processor. And the main responsibility of this processor is to manage the power on the quadrotor and interacting with the radio module. So when you send down new code, you flash this, what you have here. So the communication will go through this processor when you update the program for that processor. So this, I would say, is a typical structure for such a system. And these days, I think I can... So a course like this, we talked about embedded control. If you go back 10 or 20 years, this course focused a lot on how to manage with limited resources in the processor. So typically you had a processor without floating point unit. We will come back to that, what we mean by that, but basically how you can calculate with real numbers. So then you either had to emulate. The only thing that was supported in the hardware was to do arithmetic operations on integers. 1, 2, 3, 4, 5. So if you had real numbers like 1.552, for example, you needed to represent that using integers. So you couldn't do calculations on them directly on the hardware. But these days, I think it's fair to say that processors have become so powerful and it's very often now that even very cheap processors, they have floating point units. So I think we don't need to spend so much time on those aspects any longer. So you can just assume that you can do fast operations on floating point numbers in the processor as well. And this is the case for this processor as well. So I think also mentioned everything here. Yeah. So inside the IMU, you will have an analog to digital conversion. So the accelerometer, the forces that the accelerometer senses and the angular velocity of the gyro, that is turned into a voltage that are then transformed into a number by the analog to digital conversion. And that can be done with different kind of resolutions. So depending on how many different bits that will be used to represent the force or the angular velocity. So in this case, you have a 16-bit analog to digital conversion unit. So 16 bits means that you have a number with 16 binary variables. So you can represent everything from 0 to 2 raised to the power of 16 minus 1, which will be 65,535. If I calculated correctly. Yeah, so I would also like to mention, you probably heard about the Raspberry Pi, which is another popular architecture that you can use for if you do your hobby projects. So it's even more powerful than what we have in the Crazyflie. So it has a quad-core processor, meaning that there are 4 different computing cores inside the processor, so running in parallel. So it's clocked at 1.2 gigahertz. So it's almost 10 times as fast as the processor we had in the Crazyflie, and it is a 64-bit processor, so meaning that all the registers that you have, all the calculations are done on 64-bit numbers. And it has 1 gigabyte of RAM. And it's a graphical processing unit, it has different buses to communicate, floating point support in hardware, and you can run Linux or Windows 10 on this, and you can go and buy it. I looked it up at Shell & Company, and it was 349 crowns. So you get a lot of computing power for a very, very small cost here. So once again, since engineering time is important, in most cases, if you don't have really, really huge volume, it's better to use a more powerful processor and then save the time you spend on engineering your products. Yeah. One more thing. We will come back to that. But on this main processor here in the Crazy Fly, we are not using Linux or Windows. Instead, we are using another operating system called FreeRTOS. So this is an open source operating system. You can go and download all the source code. In fact, you will have access to all the source code. And this operating system is capable of running parallel tasks, and it has a scheduler that will decide when to execute each task and how to synchronize the work between the different tasks. It's a quite nice system, actually. So, but we will look more into the details of how that is built up later in the course. Since you have a very different background in this, I wanted to start from basically scratch. So I would say a few words about bits and bytes and how to represent numbers in a computer. So this might be very familiar to some of you. So we usually talk about numbers in the base 10, right? So we have a position system, so the last here is you take this digit 1 times 10 to the power of 0, and then this one will be 1 times 10 to the power of 1, and so forth, right? So, and with binary numbers you do the same thing, but just that you have the base 2 instead. So 11, for example, will be then 1 times 2 raised to 0, which will be 1, plus 1 times 2 raised to 1, which will be 2, plus 1 times 2 raised to 3, which will be 8. So 8 plus 2 plus 1 will be 11. And this is how the numbers are represented inside the computer. And sometimes when you see computer programs, you also see numbers represented in as hexadecimal numbers. So then you have the base 16 instead. So meaning that basically four bits, so these are called bits, each binary number here will be represented by one hexadecimal number. But then it's built up in the same way. And of course it's important to remember that it's the same number, it's just different ways to represent it. Okay. So how do we represent integers? Yeah, we already talked about it. So we have these different bits here, and they are represented in base 2. And in a computer, you can have the least significant bit to the right or to the left. So that depends on the computer architecture. So that might be different. But let's assume in this case, as we usually do, that we have the least significant bit to the right. So then it will be as I just explained here. So 11 is represented like that. And then when we do addition of binary numbers, we do it in the usual way. So if we would like to calculate 11 plus 3, we do it bitwise. So we start at the least significant bit, we add it, so 1 plus 1 will be 2. And 2 represented as a binary number is 1, 0. So then you have a carry over here, you will have a 1 here, and then you put a 0 here. And then you add 1, 1, 1, which will be 3, which will be 1, 1. So you put a carry over 1 here, and then you put the least significant bit here. And then 0 plus 0 plus 1 will be 1. 1 plus 0 will be 1. So now you got 1, 1, 1, 0, which you will interpret as 0, times 2 raised to 0 plus 1 times 2 raised to 1, and so forth. And you will get 14, as we expect, right? Okay, so this was all fine. So how do we then represent negative numbers? You know that? So, of course, a naive way would be to just have an extra bit that represents the sign. So then if it was, the last bit would be 0, it would be positive, and if it was 1, it would be negative. But the drawback with that is that that means there would be 2 ways to represent the number 0, which would sort of complicate the implementation of the arithmetic operations in the hardware. So what is typically done is that you use the 2 complement method instead. And then in the 2 complement method there will only be one way to represent 0. And in this method, if you would like to have the negative representation of a number, then what you do is that you invert all the bits from the positive number as you saw before, and then we finally add 1. So, given an example here. So let's say we can take 2, right? So 2, we are represented like this. So we have, a 1 here. And then if you would like to represent -2, then what we do is that we invert all the bits first. So we will get 1, 1, 1, 1, 1, 1, 0 instead of a 1 here, and then a 1 here. And then we add 1 to that. So then we get this representation instead. And if we do this, we can represent, if we have n bits, we can represent any number between -2 raised to the n minus 1 and 2 to the n minus 1 minus 1. And what is really useful here is that you can then implement addition and subtraction using the same hardware in the same way. So we'll do an example of that. 0 is of course represented in this way. The largest possible positive number is all ones here, and the largest negative, so 127, and minus 127 you will get by then inverting all the bits and adding 1, so you will get that one. And minus 120, so you have minus 128 you get by this. Okay, so if you now would like to do some arithmetic operations here, so let's say we would like to do subtraction. So we would like to start with 11 and then remove 3. So we can think about that as 11 plus minus 3, right? So what do? We represent 11. In this 2 complement method, it will just be as before. And then we represent minus 3 using the 2 complement method. So we take 3, invert all the bits, add 1. We get this. And then we just do addition in the normal way. So 1 plus 1 will be 1, 0. Then 1 plus 1 will be 1, 0 again. So 1 here, 0 here. 1 plus 1, 1, 0. And then 1, 1, 1. So you get 1, 1. And then you will get 1 plus 1, which would be 1, 0. And then you just throw away the 1. So what you have here in the last 4 bits is the result. So you will get 8, right? Which is what we expect. And why do you need to worry about these things? So you will later on program in C, and in C you can get access to all the bit fields of the numbers. So then it's important to know how the numbers are represented here. So that's why we talk about this. So, but this was all about integers, and I think that was, familiar to most of you. By the way, how many of you have worked with the two complement method before? Just curious. Yeah, most of you, yeah. But not everyone. Okay, so then it comes to floating point numbers. So now we would like to represent decimal numbers, real numbers, in hardware as well. And then there is a ANSI IEEE standard for that, that I will try to describe. And then floating point numbers can be represented using in single precision, so that we have 32 bits, or in double precision, that we have 64 bits. And then from the standard it's decided that if you have a 32-bit or a single precision number, you will use 8 bits for the exponent and 23 bits for the fraction part. So we'll come back to that. And for the double precision, it's 11 and 52 bits instead. So basically, all the bits are divided into these three parts. You have a sign bit, you have an exponent, and a fraction. And the value of this number is then the sign bit times 2 to the power of e. And e here is then the exponent, the bit field here, interpreted as a decimal number, minus 127. And then you have the fraction part here in binary. So m is equal to 1 point the fraction part. So basically for all the bits that we have here, so this will be represented as 2 to the power of minus 1. The next bit will be 2 to the power of minus 2, minus 3, and so forth. So, if we look at a concrete example here, representation, when we would like to represent this number, and now it's in single precision. So, this is a positive number. So, positive numbers, then the sign bit is 0. So it's just decided by the standard. And then we have an exponent bit here, so which will be minus 3. And then the fraction part here will be 0, 1. So it's represented like that. So this, as I mentioned, this was 2 to the power of minus 1. This is 2 to the power of minus 2, which will be 0.25, right? So the fraction part then will be 1.25, since it was 0.25 here, from this formula. Okay, and then we had 2 to the power of minus 3. So it will be 1 over 8 times 1.25. So this way we get this number. Right? So at least given that you have a bit field here, you can easily calculate what number it represents, right? So there are some surprising results here, and that is, of course, you have a finite number of bits here, right? So you can't represent all real numbers. But there are some familiar numbers that we can't really represent, and one such, is, for example, is 0.1. There's no way to represent that number exactly using a floating point representation like we have here. And this, of course, is important, so because when you write programs and when you compare floating point numbers, you should be very careful. Because you can calculate the sum number in different ways, and they can be represented in you will get different results. So never use equality when you compare floating point numbers. So typically you would like them to be not exactly the same, but you would like to compare if they are close to each other, or if they are greater or less than a certain threshold. So this is of course different from integers, where you can easily compare them. They are equal to each other. So, what else? There are some special cases. So with floating point numbers, actually we have this drawback here that there are two ways to represent the number 0. So we can have +0 and -0. So of course this is an extra complication that you need to deal with in hardware, but floating point numbers are much more complex in the hardware anyway than integers. But still there are support in the hardware to do these calculations today in most of the processors. There is also a way to represent infinity. So for example, if you divide a finite number with so you can divide an infinite number with a constant number, and you will get the right result. So you will get 0 in this case. There is also a way to represent if the result is not well defined. So then you can get not a number. So for example, if you divide 0 by 0, then this will internally be stored as a not a number. So if you continue to do calculations, it will continue to be not a number on these things. So that was with representation of numbers. So do you have any questions about this, or something you have been thinking about? So this was of course just a very quick introduction to how numbers are represented. Otherwise we leave this part and we continue on with how you represent the memory architecture inside the processor. And the reason why we will talk about this is that some of you have only programmed in MATLAB, for example, and there you don't even need to declare variables. But now you will program in C, and in C it's important that you declare the variable. You need to specify, is it an integer, is it a floating point, how many bits will be used, etc. And if you start to make arithmetic computations and you mix integer and floats, strange things can happen. So it's really important that you are aware of these things. And we will talk about the C, which is the sort of standard programming language for embedded systems. We will talk about that next week in more detail. But we will start to talk about these very basic concepts today. Where are the variables located inside the processor? So we will just use as an example here. So this is not the Crazy Fly architecture, but it's another processor. And it's a little bit interesting in the sense that it's an 8-bit microcontroller with a 16-bit addresses. And in this architecture, you have something called the arithmetic logical unit. So this is the part of the processor that actually does the calculations. And it does the calculations by doing operations on numbers represented in the registers. So the only thing you can do in a processor like that is to add or do arithmetic operations on values that are stored in registers. And the registers are a special part of the processor, and you have typically a limited amount of them. So in this case you have 32 registers only, so you can only store 32 numbers inside the processor, and each of them are of 8 bits. So that's why we said it was an 8-bit microcontroller. But you also have the main memory, the random access memory, and in this case it's 1 kilobyte, and you can address numbers inside this RAM, and each number here will have an address, and in this case you use 16 bits to represent that address. And when you want to do, for example, if you would like to add 2 numbers that are represented in the RAM memory, what you do is that you first have to move the values from this RAM into one of the 32-bit registers that you have. So first you move the one number, and then you move the second number, and then you ask the ALU to do the addition or subtraction or whatever it is. And then you will get the result in another register, and then you have to move it back to the main memory. Right? So you need to, so this is usually something you don't have to worry about, moving numbers from the main memory to the registers. This is done by the compiler itself, so it will generate instructions for the processor for how to do these things, and it will decide on which registers it will use and so forth. So this is very low-level stuff that you can usually not worry about. On the other hand, if you are writing programs that are very computational intensive, you would like to make sure that you optimize it in such a way, because moving data from the memory to the registers is a quite expensive operation. So you would like then to reduce the number of moves between the main memory and the registers. So you would like to household, so to speak, with the registers that you have. So if you can avoid a move, you will save a lot of time. But in most cases, you don't have to worry about these things at all. It's done automatically in a rather good way for you. What else? So inside this main memory, you will have the program itself that you have written. You will also have the variables that you need for executing the program. So they will also be stored here. And how do you know where in the program you are executing? That is stored in another, you can think about this as another register, so it's called the program counter. So it will store the address to which instruction you are currently executing inside the main memory. So in this case, so the program can be in the main memory, or it can be in a special memory called the flash memory, so which you typically don't have on a computer like this, but that you can have in a microcontroller here. So with the flash memory, so in the Crazy Fly, for example, there is a flash memory. So it's a certain memory, so it will keep its state even though it will have no power. So when you plug in the power again, it will keep, the program will still be there for you to execute. So the normal memory that you have here, if you lose power, everything you have here will disappear. But in the flash memory, it will remain. Yeah, and then another thing is that you have then the different IOs here. The way you access them from the program is that they are typically memory mapped. So if you have an analog to digital conversion and you would like to read the value after the conversion to a digital number, then you contact this digital conversion unit it will actually store its value in one of the registers, at a certain address in your memory. So it's memory mapped. So the only thing you need to do is to read a value like you read any other variable, but you just need to know which address that you read from. And the address is just a memory location here. And as we said, we had 16 bits addresses here, meaning that we will have, so here we have hexadecimal numbers. They are represented in this way. And then we just interpret, so yeah, it's just a number here, which is just a address. We can think about this as a large vector, and then which place we would like to read is just by the number here. So that's the index into the vector, the address. So that's how you interact with the environment as well. And you do the same thing, for example, if you have the pulse width modulation. That's also, you write what should be the duty cycle, you write that to one specific memory location. And then it will change. The behavior will change. Okay, so we have the main memory. We talked about that. So it has starting at some address. First, typically we have the registers, so we can access those, and then we have this SRAM memory here. And then something we need to know about is that when we execute a program, for example, now when we execute a function, so a function can, or a method, or whatever you call it, it can have local variables declared. So, and where will the local variables be in the main memory? So they will be put on something called the stack. And the stack is just something that will, so it can grow from the bottom or from the top. That's something that is decided by the architecture. But you allocate a certain part of the memory to represent the stack. And the stack is an abstraction of it's a sort of a queue. So, but on a stack you can only put things on top of it. So you add a new number, it will put on top of the stack, and then when you add another number, it will be put on top of the previous number, and so forth. Right? So you can only add numbers to the top, and you can read numbers from the top. You can't do anything else. You can remove numbers, of course. I think we can start with some C code here. So this will be new to some of you. But what we do here is that we declare a variable, x, and here we define its type. And there are different types. We will come back to that next week. But this is a character type that will represent 8 bits. Right? So you can represent numbers from 0 to 255. So 256 different numbers. And when this is compiled, when it's done like this, if it's not inside the function, it's just part of the outside any function, it will be put, the compiler will allocate this to a certain address in the main memory. So it will put x at a certain address. It's a little bit more complicated than that in reality, because it's not really done by the compiler, it's done by the loader. But in principle, it will be put on some memory location here. Okay, and then what do? We assign x the value that we have here, which is a hexadecimal number, 20. So we will have the last 4 bits will be 0, and then the 5th bit will be 0, and the 6th bit will be 1, and then the other bit 0. Okay, so we will, at this memory location that has been allocated to x, we will store these 8 bits, right? So at some address in the memory, we will go in and store the bit field represented by this hexadecimal number. Okay. So, you saw here, now it was just the character x. Now we will do something else. We will add, so this is all C notation, we will add a star in front of x. And now x is not representing a character any longer. It is representing an address to a location where a character is stored. So x stores then an address. Now, so in this case we said that the addresses were 16 bits. It was an 8-bit architecture with this 16-bit data bus, or address bus. So x in this case will be allocated inside the main memory here, and it will use 2 bytes. So 1 byte is typically, or is 8 bits. So we will have 2 bytes here because it was 16 bits. To store this. Okay, so if we now write like this, y is equal to star x. What does that mean? So remember now that x was an address, and now when we put the star before here, we will look at what is the value at the address pointed to by x. So x is a value, so it contains these addresses, and now we will assign to the variable y, which is a character, so it's stored at some point in the main memory. We will take the value at the address x and copy into the location where y is stored. Right? So y stores the value, x stores the address. They have different sizes. So the address is 16 bits, the values are 8 bits. Okay. Now it can look like this. So once again, x is an address, y is a value, 8-bit value. And if you put the ampersand mark before a variable, then we will get the address to the variable. So once again, y is stored at some address here, right? But y represents the value. If you now would like to have the address, we put the ampersand before, we get the address, and now we can store that into x, because x contains addresses. Okay, if we now write star x, so then x was an address, we put the star before, so that means that we will now go at the location pointed to by x, we will store this value. What will happen to the value of y here?
It will be 20.
Yeah. So it will now contain this value, because x contains the address of y, and now we will just go into this location that was pointed to by y and store the value. Yes. So please ask questions about this, because it can be, I assume it can be a little bit tricky the first time you see it. But it's important to remember the difference between the value of a variable and the address of the place where that value is stored. And in C it's important to know this difference, because you can pass values around between functions, or you can pass addresses to variables around. And that will be completely different. And if you have only programmed in MATLAB, for example, before, this will be very different, or you haven't been having to think about these things before. But when you program in C at a lower abstraction level, you need to worry about these things. And you could of course ask, why do you need to worry about these things? You don't need to worry about it in MATLAB. Is it really important or not? But for example, if you have a really huge data structure, have a really large matrix, for example, that you would like to send to a function. If you send the matrix itself, it has to copy the whole matrix. And if the matrix contains hundreds of thousands of elements, this will be a considerable amount of time to do that. But if you can instead just send the address to the matrix, then it will be much, much more efficient. And as I said, so that's one aspect, this performance aspect. The other aspect is that when you need to interact with the hardware, that's not something you do in MATLAB, to access the different I/O modules that you have, you will find them at certain addresses. So that is fixed where they are. You can go in the data sheet and read at what address do we have the AD converter for the accelerometer, for example. So then you need to do these things. Okay. If it looks like this, so now this is a C program. So in C there is always a main method. So when you start a C program, it will start to execute in the method called main. And here we see that the main method will return an integer. So that means it can inform the operating system about if this executed successfully or not. So typically 0 means that everything was fine, and then you have something else if it was some other number if it didn't execute as expected. And then it takes an argument here, and in most cases, if you run the program in Linux, you can send parameters to your program, to arguments to your program. And then you can, they will be passed in here in a different way. We will come back to that, how that is done. If you don't care about the arguments, you can just put void here, meaning that you, I don't care about it. And in this case, then you have these curly braces here. So, and between the curly braces, you will have the implementation of that method. So in this case, we see that the variable z here will be equal to the return value of the function foo. And foo is declared up here to return a character, in this case, an 8-bit variable. And it doesn't take any arguments. And then we have the implementation here. So then we will have x, which will be an address to some character. We will have y, which is the character itself. And then we do something here. So x is equal to, so we define the address here. And then we store into y the value stored at this address. Right? And then we return it back. And then we also have character z here, which is a variable not declared in any function. It's outside, it's a global variable that you can always access. And now it's important to understand, where are x, y, and z located in the main memory? The character z here will be, can I ask you to? So z here is a global variable. So it will be put at some location here in the memory. Oh, welcome.
Hi.
Hi. So yeah, we are just doing 5 more minutes, and then we. So meet Carl, the Chalmers philosopher, as I have introduced you. Yeah. So Z is located at some point in the in the main memory. But where are x and y located in the memory? The problem now is that you can have foo. So in principle, you could have foo call another function, which in turn could call another function. In fact, foo could call itself again. So that's called recursion. So you don't know beforehand how many instances of x and y you need to create. And this is the reason why you have this concept of the stack, as we talked about before. So what will happen here is that when you call this function, x and y will be put on top of the stack. So the stack was growing from the bottom, like this, right? So the first time, in this case, I assume that x will be put at this location, and then you will have y on top of that. And then you will do the computations here. And you will then return y. So y is here a value that is returned by this function foo. So this will also be put on top of the stack. So when this has executed, y, the new value, will be on top of the stack, the topmost element in the stack. Right? And now what will happen is that when you return back, you will assign z, which is at some arbitrary memory location here, not in the stack. We'll copy the value from top of the stack to the z value, or to the z variable. It's also important to remember that x was 2 bytes, y was 1 byte, because X contained addresses in this case and Y contained 8-bit values. I think that was the answer to the question. So what is then meant by the following code? Yes?
We get a break before the exit tournament.
Oh, it's not afternoon, right? No? Oh yeah, you're right. Sorry, my mistake. I was so excited about talking about these things. Yeah. Good. So I'm sorry for this. Just messed up. So that explains why you are here as well. Yeah, I thought you were really early.
Running inside.
Yeah. Okay, so can we take 7-minute break? Is that okay?
Yeah.